So I know I promised that we were going to go on to talk about Kirchhoff's rules for complex multi-loop circuits, but as long as we're here, I thought there was a couple more things we should cover before we go into that. One is, if you remember back in chapter 24 when we were talking about capacitors, we actually skipped over the rules for adding capacitors in series and in parallel because we hadn't talked about circuits yet and it didn't seem to really make sense. Now I think is actually the time to talk about that. So if we think back to the expression for the capacitance for a parallel plate capacitor. That expression was that the capacitance, if the area of the capacitance is the area of the capacitor, the plates is A, and their separation is D, that the capacitance of that parallel plate capacitor is epsilon 0 if there's just vacuum in between times the area divided by the separation. Compare that to the resistance of a piece of wire of cross-sectional area A, length L. The resistance of that wire is the resistivity of the material times the length of the wire divided by the area. And if we look at the role of the area in these two expressions, the resistance is inversely proportional to the area. The capacitance is proportional to the area. The resistance is proportional to the length, so adding a bunch of resistors together is in series is the same as just making a really long resistor. Likewise, adding capacitors together in parallel is like just having a capacitor with a bigger area. So adding resistors in series, R total equals R1 plus R2 plus R3. Adding capacitors in parallel, the capacitances of these are C1, C2, and C3. The total capacitance of these capacitors in parallel is C1 plus C2 plus C3. You might guess that because of the inverse proportionality, the opposite is true, that if resistors in parallel with one another, you determine the total resistance with the equation 1 over R total equals the sum of the individual resistances R sub I. That for capacitors in series, we use that same rule. So if you've got capacitors C1, C2, and C3 in series with one another, the total capacitance is equal to 1 over the sum of the inverses of the capacitances C1, C2, C3, and so on. So the rule for adding capacitors in parallel is similar to the rule for adding resistances in series. You just add them up. The rule for adding capacitances in series is similar to the rule for adding resistors in parallel. It's 1 over the sum of the inverses of the individual capacitances. So all you need to do to remember how to add up capacitors is it's exactly the opposite of adding up resistances. Let's do one example just to see how that works in practice. Can you see through that paper if I flip it over? Yeah, I'll use a different side. So let's take a circuit with a battery. I don't care how many volts. Let's say 12 volts. And parallel plate capacitor C1, two parallel plate capacitors in parallel, C2 and C3, and another parallel plate capacitor, C4. And let's give these some values. Let's say C1 is equal to 3, I don't know, let's choose some small number of farads. Let's just say microfarads. And C2 is equal to 4 microfarads. And C3 is equal to 2 microfarads. And C4 is equal to 1 microfarad. So what's the total capacitance of the effective capacitor made from these 4 capacitors in a combination of series and parallel? Well, you start with the most smallest and easily subdivided part of that circuit, we will consider the capacitance of these two capacitors in parallel with one another, Cx. And because they are in parallel, and being in parallel effectively just increases the area of those capacitors, Cx is just going to be equal to C2 plus C3. Okay? Capacitors in parallel being like resistors in series, you just add them together. So C2 plus C3 is equal to 6 microfarads. And now we can view the whole circuit as C1 in series with Cx, the effective capacitance of those two capacitors together, in series with C4. So C total for these three capacitances in series, you use the same rule as resistors in parallel. We're taking 1 over C1, which is 3 microfarads, plus 1 over Cx, which is 6 microfarads, plus 1 over C4, which is 1 microfarad, 1 over that. Right? 1 over this equals the sum of those inverses. So let's see what that is. We've got 3 inverse plus 6 inverse plus 1 inverse. We don't really need to take one of that's 1.5, and 1 over 1.5. That's 3 halves. 1 over that's 2/3. Right? So it's going to be 0.66. So the total capacitance is 0.66 microfarads. Okay, so once you get adding resistors down, the process of doing the same thing for capacitance is just remembering that the rule is flipped. Capacitors in parallel, you just add up the capacitances. Capacitors in series, you use the rule that 1 over the total capacitance equals the sum of the inverses of the individual capacitances. I might assign 1 or 2 problems from chapter 24 just for practice, but if you can do this with resistors, you can definitely do it with capacitors as well.